had been discussing crystal imperfections and we were talking about dislocations. Just to remind as to what we were doing in the last class, in the class before we did discuss the point defects which were in thermodynamic equilibrium, and by their presence they lower the free energy of the crystalline solid. But dislocations, like other imperfections as well, are not in thermodynamic equilibrium. Thereby they have a tendency to go out of the crystal whenever they get the opportunity. In this course we shall also learn as to how these dislocations come about in a crystal. And once they come, it may not be easy for them to get out. So they are there, not in equilibrium. And we saw yesterday that dislocation is a boundary between the slip part and the unslipped part of the crystal lying over the slip plane. And also we saw the slip plane is the plane which contains the two vectors, the Burgers vector of the dislocation line and the dislocation line vector itself. And we also described that Burgers vector of a dislocation gives the direction and the magnitude of the slip, which is actually a relative slip between the slip part and the unslipped parts, and it is an important characteristic of a dislocation. We saw its relationship in the edge dislocation with the screw dislocation and the mixed dislocation. And also we saw that to determine the Burgers vector of a given dislocation, we draw a Burgers circuit, which is a circuitous path drawn through the perfect parts of the crystal such that the net displacement along the path is 0. So we counted those steps and we saw that in the last class. However, to avoid any kind of ambiguity in getting the B vector after we have arbitrarily chosen the T vector, we use the right hand screw notation in drawing the Burgers circuit. And then the Burgers vector is a closure failure of the Burgers circuit. In the case of positive edge dislocation, that's how the symbol is, and the relationship between T and B is this. And this, if you look at the arrangement, the part plane comes and stops in the crystal at the slip plane. This is where your slip plane is. Similarly, the negative dislocation in here, T and B are related like this, and the arrangement here and here is the slip plane and part plane is coming from the bottom. So that's the configuration for the edge dislocation, positive and negative. Then similarly we have seen the screw dislocation. The positive screw dislocation we represent like this, and here the B vector and the T vector are parallel. Well, I'll just show you the arrangement. and there will be vertical planes in the front. That's the configuration for, and the dislocation line is right here. So here the dislocation line is. You can take the T vector going out or T vector coming in, whichever way you want to take. Well, similarly, the negative dislocation, he said we represent like this, and the T vector and the B vector are related in this fashion, which is anti-parallel. And this configuration I showed you yesterday. Sorry. And so on, so it will go. So that's the negative screw arrangement, and that's the positive screw arrangement. And the relationship, well, of course, the, as we said earlier, dislocation line is here. You can take the T vector going in and then draw the Burger circuit to get this. However, in the mixed dislocation, dislocation line is not a straight line, it's a curved line, right? In here, let's say this is my slip plane, and I said slip plane is the one which contains both the B vector and the T vector, alright. This is a curved line, this is my T vector. Let us say my T vector goes in this direction. So here the T vector is going in this manner, here the T vector is going out in this manner, and the B vector, the dislocation line is this, it remains same everywhere. So it becomes here a positive screw, in here the T is like this, B is like that, this would be what? Negative or positive?
Negative.
Yeah, it would be negative edge dislocation. Okay, and in here the B and T are, see, let's put a tangent T like this, but B is still there like this. Angle between B and T is going to be this, because that's B and this is T. So it's partly it is an edge dislocation, partly it is a screw dislocation. Okay, because B can be resolved along T, the component of B along T is here, that shall give me a screw component, and the one which is here along this shall give me the edge component. That B vector can be resolved. So it is partially a edge dislocation, partially a screw dislocation elsewhere. That's what is a mixed dislocation. Well, in the case of screw dislocations, we had the shear stresses or shear strains around the dislocation. That's the dislocation. Here bonds are strained because one atom is here, another one is there, which were actually bonded like this earlier. They were bonded like this. Now the bond is sheared. Instead of vertical bond, it's become slightly tilted, right? So in the case of edge dislocation, of course, in the case of edge dislocation, there are compressions here and tensions there. Similarly, there are tension here and compression there. They are principal strains. However, in the case of mixed dislocation, I shall have the mixed state of strain, I shall have both, or a general state of strain. I could have shear component, I could have principal component. Okay. All right. So next we shall like to see some more characteristics of this dislocation line. We have also seen this with the mixed dislocation. We try to work out the Burgers vector of the mixed dislocation line at two places, and we found that to be same. So the Burgers vector of a dislocation line is invariant. It doesn't change with the location of the dislocation, whether it's a mixed dislocation or a edge dislocation, screw dislocation, it doesn't change. At all locations along this, it is the same. So let us say I have a dislocation line going like this. Let's define the T vector in this manner. It will be going like this, the T vector. Let us say the B vector of the dislocation line is this, right? At this location, can you tell me what is this segment of the dislocation line which are marked? What is the characteristic of the dislocation line there?
So it is screw.
It's a screw. B and T both are parallel and it would be positive screw. Alright. Similarly, let us ask me about this component here.
It is a negative edge dislocation.
Yes, it is going to be negative edge dislocation. Very good. Because T is going down here and B is this way. From B to T the angle is 90 degrees, 270 degrees. So it's a negative. Like this you can find the character of the dislocation line which is varying from place to place. But the Burgers vector is not changing. Alright.
So in some cases it would have, it won't be 270, not 90 and not 0. Then
The mixed dislocation. It's mixed dislocation, right? What you are asking is, and this is state, this is T vector and this is B vector. This is a mixed state of dislocation, general dislocation. It has shear strains, it has compressive and tensile strains. The principal strains and shear strains, both are there. Therefore, it's a mixed state of strain. It's a mixed dislocation right here. This segment is a mixed dislocation, right? Or mixed dislocation, you can also say the general dislocation. Now, if there are dislocations meeting in a point in the crystal, say for example, there is a dislocation line here and there is another dislocation line like that and a third dislocation line going like this. They are all meeting in a node here. So this dislocation is going toward the nodes, then the T vector is this, going towards the node, T vector is this, and going towards the node, T vector is this. So T vectors are chosen like this. Either I take them going towards the node or I take them going away from the node. In either case, if I work out the Burgers vector and sum them up, the sum of the three Burgers vector would turn out to be 0. Right? That is, let us say the Burgers vector for 1 is this, Burgers vector for 2, okay, let us start from 2 for this here, and the vector, this is B1, B2, and this for the B3. So the total sum of the three vectors would be 0. Okay, you start from here, B1, add to it the B2, add to it the B3, the net UD come back, the vectorial sum is 0. That's the meaning of it whenever there are dislocations meeting like this. Another important thing which I've talked about, the dislocations meeting in a node inside a crystal, because they could be curved linear lines and they usually do form a jungle of dislocation in the crystal. Dislocation line cannot end abruptly in a crystal. Either they end in a node inside the crystal like I showed you just now, or they end on the surfaces which I showed you earlier pictures, edge dislocation, screw dislocation, and the mixed dislocation. The ends of the dislocation line, straight line or the curved line, they are on the faces of the crystal. So they are coming out and ending on the surface of the crystal. Or dislocation can close on itself as a loop. That is, suppose this is the slip plane. In this slip plane, I could have a dislocation line like this. You can choose the T vector, whichever you take, clockwise or anti-clockwise, whatever you want to take. And then let work out the B vector. You will see where there are some places will be edge, some places screw, otherwise it will be mixed dislocation. Loops can form like this. Then it's important to understand why it is happening. It's happening because it's a boundary between the slip part and the unslipped parts of the crystal lying over slip plane. That means what I am trying to say is that this inside is the slip part, inside the loop, and outside the unslipped part. Two are distinct regions. It's possible to say that. Let's say now when the dislocation ends on a surface like this, let me say is the slip part of the crystal, and that's the unslipped part. Clear cut demarcation between the two parts of the crystal. Right, and when it meets in a node, like this, then there are three parts, there are three of them meeting. One is slipped relative to the other, and this is slipped relative to this. Distinct regions are there, and the continuity is provided by the node where there is no displacement, and therefore the sum of the three Burgers factor turns out to be 0. Otherwise the crystal would not have a continuity. There will be some kind of a discontinuity there at the node, which cannot happen. So this is relatively slipped with respect to that, while this is relatively slipped with respect to the other two. So slipped part and the unslipped regions of the crystal are very well defined. Then only I get the boundary, and that's the dislocation line. So in other words, what I am trying to say is I cannot have a situation where I have a dislocation starting from here and it stops here in the crystal. Which is the slip part, which is the unslip part? Can you define? You cannot. Right here when you come, you get into trouble. This is the slipped or this is unslipped. Which one is this? This is the same region. So that is not allowed. That's not possible. No dislocation can end inside the crystal abruptly like this. Right? Now we have seen there are strains associated with the dislocation line, whether it is edge where there are principal strains, screw dislocation where there are shear strains, and a mixed dislocation or a general dislocation, general state of strain. Whenever there is a strain, there will be some stress in the bonds. Bonds are strained means bonds are also stressed. There is a stress acting on it. There will be some strain energy stored. I consider elastic strain energy and work out the model. Just simply say the energy per unit length of the dislocation line is one by 2 mu times the magnitude of the Burgers vector square, right? That's the energy of the dislocation line per unit length. Multiplied by the length, you will get a total energy stored in the crystal.
What is mu?
Mu is the shear modulus of the crystal. B is the magnitude of the Burgers vector. Right? This is you can see a parallel of this when you see the Hooke's law. This is the stress, this is the strain. Energy per unit volume is here. It is 1 by 2 sigma times epsilon, and you know Hooke's law is obeyed, so sigma is equal to Young's modulus into epsilon. If I substitute this sigma by Young's modulus into epsilon, this becomes 1 by 2 modulus times epsilon square. Do you see that I have not derived the above relationship, but I am showing you how it is got. B, the magnitude of the Burgers vector, is the amount of displacement. This is the measure of the strain. Mu is the shear modulus, okay, which is because I am talking about the shear taking place. So that's, instead of modulus I am using as Young's modulus, I am using the shear modulus. So that's the energy or elastic strain energy stored in a dislocation line, whether we will take this as this model irrespective of whether it is an edge dislocation, screw dislocation or mixed dislocation. There is a small difference between them, the energies for an edge and screw, but we shall keep using this formula, okay. In this course we shall use only this one. Now from this energy you can see that half mu b square, and I already told you that dislocations are present and they are not in thermodynamic equilibrium, meaning thereby by their presence they are increasing the free energy of the crystal. So tendency of the crystal would be to have as small an increase as possible for every dislocation. So dislocations would like to have as small an energy as possible. Shear modulus is a characteristic of the material, and I told you it is structure insensitive property. We shall see what decides its shear modulus or the elastic modulus. But Burgers vector mu b square by 2, b square, if you can minimize, that should be the minimum energy of a dislocation line. That will be a little more stable dislocation, that kind of a dislocation in the crystal. So I am considering the monatomic FCC crystal, and what is the smallest distance between displacement which you can do from one location to another for an atom in FCC? Smallest displacement you can do is from corner to the face center. So which I can write as 1 by 2 of 1 1 0. Any phase diagonal, 1 1 0 family when I write, it could be any phase diagonal, right, half 1 1 0. Similar in BCC, what is the minimum displacement? Corner to the body center, let's say that, and this is represented in terms of Miller indices 1 1 1, and that's the magnitude, right. Similarly in simple cubic, magnitude is 1 here. And sodium chloride,
A by 2.
it is the minimum distance between an cation to anion, right, but he says A by 2, but that's not correct. If I do that, what would happen, make a part plane, what would happen is, below the part plane, ions of the same sign will come together and there will be a very strong repulsion between them. When cations come closer, there will be very strong repulsion, and that's going to be a unstable configuration of the dislocation. What provides the stable configuration is when I make the displacement so that anion goes to the anion, cation goes to the cation. That displacement is again from corner to the phase center, because it belongs to the FCC space lattice. Now you shall see the other three which I am showing. It is the displacement from one lattice point to the next which gives me the stable displacement for a dislocation line, or the Burgers vector of the dislocation line. The sodium chloride would be again like in the FCC, half 1 1 0. In cesium chloride, similarly, which is cesium ion in the body center, chlorine in the corners, displacement from corner to the body center would mean going from chlorine to cesium. That means two ions of the same sign coming together again. So we like to make the displacement chlorine goes to the chlorine, that is from the edge one corner to the other corner, and that will be again 1 0 0. This is again the space lattice is simple cubic. Same is true about diamond cubic, it will be again half 1 1 0. So these three say the minimum distance between the lattice points. So you have to look at the space lattice. And this is the minimum distance between two lattice points. Or nearest distance between two lattice points instead of minimum. If you want to call nearest, that would be, I think, more close. Nearest distance between two lattice points. So that's what is happening here, and that if I continue this is holding valid for monatomic crystals also. This distance is from one lattice point to the next, also from one lattice point to the next, and one lattice point to the next. Here the situation was simpler here because all atoms are alike, right? And again it turns out to be from one lattice point to the next, which is the nearest distance.
So can you re-explain in the case of NaCl what happens if we A by 2 is
I
2?
thought so. Okay, if you want I can do that. Alright, I need a alright, since I don't have it here. Okay, let's make sodium chloride, huh? Alright, and I place cations here. Right. Let's say this is my part plane. I make this displacement and this is my part plane up to here. What happens to the other planes? Just check that. This plane is continuing with anion, cation, anion, cation, anion, cation, anion, like that. But see now the situation just below the part plane, somewhere here. This is little far off because the bond is stretched. These are the two anions coming together, two cations coming together, two anions now coming really together. That's what is making it unstable. But if you make the displacement like this and use this as a part plane, you can draw a similar structure with starting this your cube like this. You can make a cube, make this as a part plane. You will see that when you try to make this, there is always an the opposite ion in between, which is sitting here. So anions will not come close to anions, cations will not come to cations. It is only the opposite charges will remain together. You please make this picture yourself with this orientation and make this as a part plane and see what happens. Okay? And when you make this as a part plane, either this set of cations or that set of cations will go along with the plane. Let's say take this one. Only then it is electrically neutral, this anions and these cations, because my displacement is from here to there. So whatever is in between, that is also displaced, right? So therefore this is the plane is going to be slightly thicker. It's not that, and that's what shall make it a stable configuration. Is this point clear? Okay, good. But please do sketch this yourself so that you understand what we are talking about. Not changed. It's changed. Okay, good. Let's go to the next. Next, we find the characteristics. The opposite dislocations lying on a slip plane attract each other and may annihilate each other if brought close enough. I'll just demonstrate this with the help of So this is my slip plane. On this slip plane, let me have this as 1 dislocation line. Here I have one positive edge dislocation and here I have one negative edge dislocation. Both of them lie on the same slip plane. Right? This is how the atoms are placed. It is possible for us to make them come together. There is I said there is an attraction between them. They would like to come close to each other. Let's say I try to apply a small stress like this, a shear stress. This pushing the top part of the crystal to the right, bottom to the left. It's possible that when doing so, the stress may be enough for this atom to bond with this one, so that it comes slightly to the left and this one comes slightly to the right and form a bond. So part plane comes here. Similarly on this side, now when I am applying the force this way, this is going slightly to the left and this one goes slightly to the right and they can form, and this becomes a part plane. So like this the part plane can shift and they can come one over the other exactly and they will make a perfect crystal. Right? That is, I have a dislocation like this, add on to this a dislocation like that and I get a perfect crystal. Right? And all the strains from the crystal would have gone. All the additional free energy which was there in the form of half mu b square is all gone. No dislocation is there in the crystal. Energy is lowered of the crystal. Right? So how the opposite dislocations lying on the same slip plane have an attraction towards each other. Also it can be seen like this. When I have a dislocation like this, I have compressive strains here and I have tensile strains here. Similarly, when I have added to it another dislocation like this, I have compressive strains here and I have tensile strains here. When they come together, a negative strain and positive strain they add because the vectorial addition of this, and therefore the net displacement can become 0 and ultimately I end up with a crystal without any strain whatsoever. There are no strains in it. It becomes strain free. Compressive strain cancels the tensile strain here and this tensile strain cancels the compressive strain here, and this is a common slip plane. You get a perfect crystal.
So for this they should be very close enough. Is there a limit?
No, if they are of opposite sign lying far off, there is an force attraction between them. There is an attraction. But whether they can come towards each other I'm not guaranteeing that. I'd say that let me apply the stress. By applying the stress, I try to bring them together. If I don't apply any stress, would thermal energy bring them together? It depends how high the thermal energy is. And secondly, usually thermal energy provides a random processes. Sometimes atoms are going this way, sometimes they're jumping this way, sometimes jumping up. So it is not making it go in a particular direction, right? So it may, if they are very close and you are applying stress, possibly, and the temperature is high, it may happen. I'm not saying that it will always happen. The distance is more, definitely. It's not easy for them to come towards each other.
External will have to be used.
At times, yes. And sometimes if the temperature is very high and they are close by, it can happen. Okay. So both thermal energy and the external help, both are required. Now in this location, same sign, lying on a slip plane repel each other. Obviously, if they are of the same sign, that means this compressive strain here and this compressive strain here, when they are coming closer to each other, they will add up. When the strains add up, they add up linearly. What happens to strain energy? It goes as a square of the strain. I just now showed. So it will become very high. Say for example what happens here. Right now the two dislocations on the same slip plane but are far apart, its energy is 1 by 2 mu b square, and this energy is also 1 by 2 mu b square. So total energy is mu b square. When I bring this dislocation together, close to each other, what the configuration would be? Let us see that configuration. This part plane and this part plane, both have come together. What is the Burgers vector of this dislocation line? It's going to be from here to there. It shall be 2b. If I consider as one single dislocation, what is the energy of this? 1 by 2 mu 2b whole square. That's the magnitude. So it becomes 2 mu b square. Which is double of this, compare that. So why there is a repulsion, you can see now that, because crystal is trying to have, or system is trying to have as low a free energy as possible. So by keeping them apart, the energy is only mu b square. By bringing them closer, energy becomes 2 mu b square. There is an increase in energy of by the amount mu b square, right? Therefore there is a repulsion between them. While other interactions, these are the interactions between the dislocations. Here I show you, this is a central dislocation and there is a region in the crystal around it. I talked about dislocations of the same sign lying on the same slip plane here, they repel. But dislocations the opposite sign or attractions I show, let us say by blue. These will be attracted. This is what we have talked about, right? However, when I go in a region just above this, if I have a dislocation of this sign, there would be an attraction between this and this.
So what this cross represent? This is what?
Pardon? This is a region around the dislocation line. and this is an angle of 45 degrees from the slip plane. Why this is going to attract? Should I use the blue color for that actually? Here and here, these will attract each other. They will try to arrange one over the other. Can you see that? When I have a dislocation like this, I have here tensile strains. When I have dislocation just below this, the same sign, I have compressive strains here. So I can make the bigger field of the strains. So there is a region here where there is a positive strain, negative strain meet each other and cancel. So there is a volume of the crystal where strain energy is not stored. So energy of the crystal is lowered by this. So same sign attract. Here opposite sign attract. Here opposite sign attract. Here is the same sign. Here also the same sign. So the whole region in the crystal around a dislocation line, which is straight line, are divided into 4 parts, 4 segments. By the slip plane making angle of 45 degrees, another plane here, another plane there. So between this region, same sign dislocations attract. In this region, same sign dislocation attract. While in this region, only opposite kind of dislocations attract each other. Right? So that's the interaction of dislocations with dislocations, whether it is edge, screw or anything, right? As long as the sign we are talking about is same or opposite. Now we like to look at the interaction of the dislocations with the point defects. So far we have talked about the point defects. So there's other than the dislocations, let's see how do they interact. I have just taken an example of edge dislocation. In the edge dislocation, their bonds are shorter, compressive strains are there. Here the bond longer, the tensile strains are there. So the point imperfections can be, let's say, an interstitial solute or interstitial atom. If it is an interstitial atom, it would like to find an interstitial location where it can sit without straining the neighborhood and minimize the energy if possible. Usually we told you that the atoms which we have, they are bigger than the void spaces available in closed packed structure like octahedral voids in FCC. 0.414 is small enough for even small atoms to sit there. So when interstitial atom sits, for example carbon sitting in iron, it strains the neighborhood. However, if you can find a bigger void space, it will go and sit there, it will not strain the neighborhood so much. Where is the location, where the void space which is bigger in volume? Below the part plane. You see, this is a much bigger region and it can sit here. That's the interstitial void which can sit there. Just below the edge of the part plane it can sit. Right? Similarly, I can have substitutional impurity atoms. Substitutional atoms could be smaller, could be bigger. If I have a smaller atom, if I have a smaller substitutional atom, it requires less space to sit. So where would it sit? Towards the edge, towards the part plane, right? So this is where it would like to sit. So less space is there, it requires only less space to sit. But if I have a bigger substitutional atom, If this is tensile region, it would like to sit here. Right? So this is how the point imperfections interact. Now vacancy is also point imperfection. How would it interact, the vacancy? Around the vacancy, what are the kind of strains?
Tensile.
Tensile strains. Where would it go?
In compressed.
In compressive region. If it goes in the compression region, can interact like this with it, right? All right. Now after this, we will talk about a few more characteristics. The density of a dislocation in a crystal, means the length of the dislocation line we express per unit volume of the crystal, and that is either expressed meter per cubic meter or per square meter. The way these are measured is a small difference. Meter per cubic meter, it gives the total length of the dislocation line per unit volume of the crystal. As we measure per square meter, let's say we take, usually crystals are opaque, we take a surface of the crystal, prepare the surface properly, polish it and etch it, and find out the number of dislocations intersecting the surface. This number per unit area of the surface we have chosen is what it is. The way it is measured, there is a small difference between this and this. Statistically a factor of 2, but that 2 factor we shall ignore when we talk about in order of magnitude 10 to the power 12 per cubic meter per cubic meter or 10 to the power 11 meter per cubic meter kind of dislocation length we talk about. We can ignore that factor of 2. Now well annealed crystals have a dislocation density in the range of 10 to the power 8 to 10 to the power 10 meter per cubic meter. Well annealed, what I mean by this is I have tried to keep it at an elevated temperature. Annealing gives a connotation that the crystal has been kept at an elevated temperature where the available thermal energy is high. That thermal energy tries to help the dislocations get out of the crystal. Either the same kind dislocations coming together, opposite kind dislocations coming together and annihilating, or they go to the surface and get out of the crystal, right? Those are the things, but even after doing all that, I am left with a length of the dislocation line of the order of 10 to the power 8 to 10 to the power 10 meter per cubic meter. If I have 10 to the power 8, which is usually more than 10 to the power 8, 10 to the power 8 meters means 10 to the power 5 kilometers. It's 0.1 million kilometers is the length of the dislocation line in a cubic meter of the crystal, right? It's not a small length, but the total volume which it is affecting, I said, is still very small, right? Despite this length, total volume it is affecting of the crystal is very small. Alright, then we stop here and start from here in the next class.